Hi everyone, my name is Raquel Hurtasun and I'm the Chief Scientist at UberETG, as well as a professor at the University of Toronto. Today, I will talk about the role of tracking in self-driving vehicles. The traditional software stack for self-driving is composed of a set of modules, executed one after another. Every fraction of a second, the vehicle senses the environment. This is illustrated here with a bird's-eye view of the LiDAR point cloud. The first task is then to localize the vehicle with precision of a few centimeters. This is done not only to route the vehicle to the desired destination, but also to utilize high-definition maps as prior knowledge for subsequent tasks. The perception system is then responsible for estimating where the objects are in the scene, here depicted with rectangles for vehicles and circles for pedestrians, which composes not only detection, but also tracking. The prediction system then takes the output of perception and estimates the potential trajectories that the actors might take in the next few seconds. Then the motion planning module focuses on a region around the self-driving car and estimates the safest maneuver towards the goal that the vehicle should do in the next few seconds. The control system then ensures that the trajectory we intended to follow is the one that is executed, as there might be deviations due to unaccounted factors such as friction and simplistic vehicle dynamics. This full process is then repeated every fraction of a second, typically 100 milliseconds. So given that this is a workshop about tracking, let's focus on that specific part of the stack. In autonomy, tracking is concerned with explaining the paths of the actors in the scene, be it vehicles, pedestrians, cyclists, or other types. In the video, this is illustrated with a consistent color across time for each individual actor. Tracking allows us to extract key features from actors such as velocity, acceleration, and turn rate, which in turn informs us of their potential intentions in the future and allows the self-driving vehicle to safely plan accordingly. Even though as humans are remarkably good at visual tracking, being one of the very first skills we develop as infants, it is a very difficult problem in the computer vision community. In the context of self-driving cars, we are interested in tracking multiple objects. This is typically approached with a tracking by detection framework. First, we detect objects in each frame individually. Then associate detections that refer to the same physical object across time to form trajectories. And lastly, refine their state across time in order to minimize the detection noise and produce trajectories with realistic motion. This therefore characterizes a problem with continuous aspects pertaining to box regression and motion modeling, as well as discrete aspects of data association across time. So let's start there. The discrete portion of tracking covers how to decide that a set of detections refer to the same physical object and should thus be associated. This can be done greedily by immediately associating each detection with the best pair. This is very fast and simple, but often leads to non-optimal solutions. Alternatively, we can formulate the association of pairs as a decision matrix and find optimal assignments using the Hungarian method. This is also a fast and simple method with the benefit of local optimality. To achieve global optimum, we can formulate tracking as an integer linear program describing all the frames, not just two. To achieve global optimality, we can formulate tracking as an integer linear program. And this allows us to find optimal assignments over the entire optimization window, while typically still being fast enough for real-time applications. In the next slides, we will discuss the formulations for this approach to tracking. The formulation of the linear program is done using a minimization over unary and pairwise costs. In particular, the unary costs are typically related to decisions such as, is this detection a real object or not? In here, for instance, we have very good evidence that this is a true positive. But here we have a poorly fit box with very little overlap with the real vehicle. We ideally want to use the first detection, but not the second. We also need to decide if an object does not relate to any previously seen object and thus defines a new trajectory. We see here an example of a vehicle just coming out of occlusion and into the scene, so likely an object we haven't seen before. Whereas here we have a vehicle that we have tracked for an extended period of time, as it is right ahead of us and in full view. So certainly not a new trajectory. Conversely, we also need to establish when an object defines the end of a trajectory. Here we see an object going out of view, thus ending our observations of it. While for this one, we are still likely to see it next, since it's neither leaving the scene nor close to occludence. On the other hand, the pairwise terms are generally concerned with the associations of objects. In this example, we have two vehicles that are roughly in the same location and share similar appearance features, so very likely the same physical objects. Whereas in this one will have to admit a physically invisible motion to consider them as a match. We need now to formulate these intuitions into an optimization problem that we can solve. To that end, a set of variables are introduced in order to indicate the discrete choices we discussed before. In particular, we have yi indicating that I is a true positive, y new I for I defining a new trajectory, and y end I for when it is the end. And lastly, we have y link ij when I and j are the same object. With those, we can then define the cost of a trajectory as the sum of the individual assignment costs. We have a cost for treating all detections in the trajectory as true positives, a cost for starting the trajectory at the first detection, a cost for associating all detections in the trajectory, and lastly, a cost for ending the trajectory. This gives us a total tracking cost as sum of the individual trajectory costs. However, this does not define a proper optimization problem, since the set of all trajectories, indicated here as calligraphic T, is what we want and not known a priori. So how can we solve this? Naturally, we need to define the problem in terms of units we know, which is in this case are the detections. However, we need to be careful here to produce valid tracks. So we constrain our optimization to produce non-overlapping trajectories, which we express in this set of equalities. First, if a detection I is marked as true positive, then it must, by definition, either start a new trajectory or associate to a previous detection. And it must also end a trajectory or associate it with a future detection. This thus guarantees that all detections will have a valid set of assignments and no two trajectories will share the same detection. With these definitions, we can finally describe a full linear program that we can optimize and find trajectories by minimizing the sum of all the costs subject to the constraints. This describes an offline process that, given a finite amount of observations, produces trajectories that optimally explain them, subject to our costs and constraints. However, for our application, what we really want is online tracking, such that whenever a new observation comes in, we can immediately produce trajectories with what we have seen before. This poses a challenge since the cost of the optimization will grow with the amount of observations and quickly become infeasible for real-time applications. Instead, we can find near optimal trajectories by solving for a bounded window length while reusing the computations from previous windows. You can look at the paper below for more explanations, as this is a particularly involved piece of work. We can also explore the use of neural networks to predict these individual costs and ways to train them, such as the inference process produces trajectories that are as close as possible to the ground truth, allowing us to leverage the vast amount of data we collect. This is possible through a max margin loss. For this, we first run a detector over our input to produce detections, then run another set of neural networks to predict individual tracking costs and optimize the linear program. If we then take the ground truth into account, here shown are as the shaded green box, we see that our detections were not very well aligned. And thus their assignment costs should be increased a bit. Let's assume these are our only two frames. Then certainly this detection defines a new trajectory, and so the cost should be reduced. And conversely, this defines the end and should also be reduced. Lastly, we have a pair of weakly fit detections, but they still reasonably refer to the same object, so it seems appropriate to reduce their matching cost. These increases and reductions in cost allow us to compute gradients that we can then use to update the weights in our neural networks via backpropagation. To find more details on this approach, we refer you to our paper in the footnote. We have thus defined a way to train neural networks to produce a stream of frames, first extracting individual detections independently, and then optimizing over the entire window to find trajectories. This process by itself, however, cannot correct noise from detectors, which are typically trained to regress boxes that produce the best fit for the specific frames they receive, not temporal consistency or smoothness, and associating these sets of boxes will not change that. If we, for instance, plot the angle of the vehicle as it makes a turn, we can see that our raw observations follow a noisy curve when compared to the ground truth and don't produce a realistic model of motion. Having a kinematic model is key here, as we can mathematically describe them with differential equations and adjust our observations such that they conform to the model. This is a framework that allows us to use our creativity and prior knowledge about the world to create models that follow unexpected behavior, for instance, constant velocity or turn rate and acceleration. Furthermore, we can also use different models for different actor types, since the kinematics of a pedestrian is largely different from those of a vehicle. We can go further and take the uncertainties of the observations into account by modeling the involved probabilities. This is typically done with statistical inference approaches such as Kalman filter, which models the covariance in the continuous state space, or a particle filter, which then models the full distribution. We can also take another step and model our classification uncertainty, allowing the filter to switch motion models in case we misclassify a cyclist for a pedestrian, for instance. Lastly, we might also be able to take a fully learned approach to this using recurrent neural networks. In a traditional self-driving pipeline, predicting how the objects will move in the next few seconds comes after detection and tracking, since tracking is really not the end of the full stack. The simplest method to try to tackle this problem is to unroll the tracker state with a kinematic model, such as a constant velocity or constant turn rate and acceleration. However, we can see in the cartoon that if we have a vehicle right before making a turn and showing any angular velocity, both kinematic models will fail to predict accurately. Another option is to perform maneuver-based prediction. This is a two-step method. First, the intent of the actor is classified, and then we can either use a fixed set of prototypical trajectories for each intent, particle filtering, or other approaches to obtain the final trajectory. The main downside with this traditional pipeline is that the information that gets passed into prediction and about detection and tracking, as well as the static environment, is very compact and handcrafted, and makes over-simplistic assumptions about uncertainty, causing information loss. To fix this, let's see how more recent works have tried to use neural networks to learn more flexible representations. There are many representations that were originally designed for detection that can be used for the task of motion forecasting. Waypoints of past trajectories, together with their uncertainty, if available, can be passed through an RNN encoder. Some works have also leveraged voxelized LiDAR in a local region around the perceived actor to account for geometric cues. A better option is to rasterize the geometry of the perceived traffic participants in a multi-channel, bird's-eye view image local to each actor, and use a CNN on top of that to extract actor features. For the environment, map rasterizations have also been explored. Recently, approaches that exploit the relational information in the map together with graph neural networks or transformers have also been proposed. Our lane graph net model outperforms the state-of-the-art in the Argo-Verse motion forecast benchmark. Importantly, our result was submitted 3 months ago to the leaderboard and it still has the best multimodal minimum average and final displacement error, despite the fact that there was a competition in between with prices. While this great performance is exciting, the Argo-based dataset assumes that the input to the prediction system is perfect perception, which is never the case in practice. If we look back at the traditional software stack, the advantage is that we have interpretable representations and it is easy to incorporate prior knowledge. However, this traditional engineering stack has also many disadvantages. For example, reaction time is typically large as computation adds up. Furthermore, developer productivity is very low, as any changes done in one part of the stack will affect the entire stack, and engineers need to manually adjust their algorithms to account for these changes. Furthermore, the different models are not trained for the end task, and thus improvements in model performance do not translate to better driving. Instead of assuming the perception information is correct and that a compact representation can capture all details, can we instead learn a shared representation valid for the two tasks? This will lower the reaction time, produce richer representations thanks to joint optimization, and we will still preserve the interpretability of both tasks. Our work Fast and Furious was the first to show that it is possible to unify both tasks. The input is a history of previous ladder sweeps. Using the pose of the SDB at different timestamps, we can project past sweeps to the current coordinate frame. We can then voxelize the point clouds into a bird's-eye view tensor with 4 dimensions: height, width, time, and depth. Now we can run 3D convolutions using depth as features to fuse spatiotemporal information. Once the time dimension has been reduced, we can predict the outputs with 2-dimensional convolutional headings. For each pixel in the output map, Fast and Furious predicts a classification score and a series of future waypoint regressions. To obtain the final detection, we threshold the scores and apply an NMS as usual in object detectors. We then obtain a single feature trajectory for each actor by indexing the regression tensor at the positive locations of the classification after NMS. Fast and Furious also included tracking, but as a post-processing. The idea is that since we have the information about previous motion forecasts outputted by the model at early timestamps, we might as well use this information for tracking. In this fashion, the bank of tracks not only contains information about the most recent track states of the vehicle, but also the latest motion forecast. When detections from a new timestamp are available, we can compare this to the new motion forecast, to the previous motion forecast, taking into account the time difference to get a match. In this case, we use a simple heuristic that works well in practice. That is, we associate each detection to the previous forecast with highest overlap if bigger than an IOU threshold. For each association, we heuristically update the confidence of the track and the motion forecast. If a detection does not have a match, we create a newborn track. Finally, if a track is not associated with any detection, we heuristically decrease its confidence and discard it when it's below some threshold. In this video, we show the ladder point cloud together with the detection scores, bounding boxes, and the short-term motion forecast for 1 second into the future. The vehicles are color-coded according to a heuristic tracker that I just explained that matches the detection to previous motion forecast in a post-processing step. Notice how difficult the problem of self-driving is, how many actors we need to detect, track, and predict its motion into the future, and how well this approach works. Maps are an important prior for both detection and prediction. For instance, it is more likely to find a vehicle on the road than in the sidewalk. And we know it is likely that a vehicle keeps its current lane in the future. Our work in PnPNet proposed to raster the map in bird's-eye view and extract features with a 2D CNN, which can then be trivially fused with the ladder features coming from the other streams by concatenating along the feature dimension. Here, the ladder CNN is simplified to a regular 2D CNN by stacking depth and time together in the input, which yields better performance and is more memory efficient. Moreover, in this work, we show that we can also accurately predict discrete intentions by adding yet one more header that performs multi-class classification over actions such as turning right, stopping, being parked, or lane changing. This allows the planner later on to not only reason about occupancy, but also about semantics and recover the interpretability of traditional approaches to prediction. The outputs of the network are split here into 2 visualizations. On the top, we can see the same outputs as in Fast and Furious, and in the bottom, we show the high-level action prediction, which provides a more interpretable way to see the driver's intention than just future trajectories. More precisely, this gives us the probability of a car being parked, stopping, keeping lane changing, or turning. A purple bounding box means our model believes the vehicle is parked. In the spectrum below yellow and red, the redder, the higher the probability of stopping. We visualize the likelihood of keeping lane, turning, or lane changing by the length of these arrows. Just as an example, we can see here that the neighbor is very confident with a lane change is taking place. You can see here the wide variety of scenarios and the difficulty of the task. However, the single stage architecture of previous PnP models, although very fast, is not very flexible. For instance, we cannot reason explicitly about active interactions since the notion of an instance is only recovered after object detection. But these methods predict detections and motion forecast in parallel. Therefore, next, we change the architecture to a two-stage approach, where the motion forecasting model reasons at the instance level. To do so, we first extract features from LiDAR and maps just as we have done before and fuse them. Once we have rich features from the whole scene, we can obtain object detections shown in red. Let's focus on one of the vehicles. Since we know the information ahead and to the size of is the most relevant, we attribute this region of interest to the actor. Then we can pull the features on that region as the summary of the actor characteristics. We can do this process for all vehicles in parallel. We can now further process the features with a CNN with global pooling and obtain a feature vector for each actor, which is passed to the prediction model. In the results we're going to show next, we evaluate different approaches in the challenging ATG dataset, which is basically composed of many scenes that have been driven around multiple areas in North America. And they have very complex scenes with many, many actors, making it very interesting for agent-to-agent interactions. Most approaches to motion forecasting assume perfect perception in their papers, or in other words, that the ground truth path trajectory is given. As we all know, this is not realistic in self-driving cars, where we must operate with a real noisy perception system. We see two options to use them in the real world. The first one is to keep their method unchanged by extracting past features using an off-the-shelf tracker that consists of an interactive consists of IMM with unextended Kalman filtering and concurrent matching on top of the detections in the past frames. The second option is to replace the past trajectory encoders in these methods with our feature extraction pipeline and train the model end-to-end as a joint PnP model. We take three public methods that assume perfect perception: social LSTM, convolution social pooling, and CarNet, and we implemented these two versions of them. Tracking base, shown in blue, and end-to-end joint PnP, which doesn't have tracking, shown in red. We can see that the PnP adaptation of these models brings a big improvement over the traditional pipeline based on tracking that is not optimized jointly. In particular, we see reductions of an order of magnitude in the collision rate among predicted trajectories from different actors. This shows that the initial hypothesis that the traditional pipeline passes too compact of a representation to prediction is actually true, and that optimizing end-to-end gives better results. One aspect that is hard to handle from the traditional pipeline is missing data, which we encounter when either a vehicle was not detected in the past or the track was fragmented. A natural question is, can we bring tracking to the joint perception and prediction framework? This is exactly what PnPNet does, which is a new framework for joint perception and prediction that brings object tracking in the loop. Specifically, PnPNet performs detection, tracking, and prediction subsequently. For tracking, it solves both the discrete problem of data association and the continuous problem of trajectory estimation. To keep track of objects across a long time horizon, our model has an explicit memory that memorizes the past tracks, as well as their features. Given object trajectories produced by the tracker, we also propose a new trajectory representation that captures both the frame-wise observations and object motions across time. PnPNet is end-to-end trainable and benefits from multitask learning. Here we illustrate how to build a PnP model step by step. We start with a joint perception and prediction model without tracking, where we have a bird's eye view backbone network that takes the raster images of multi-sweep LiDAR point clouds and HD maps as input, and outputs object detection as well as their corresponding future trajectories. This model will serve as the baseline for PnPNet, and from now on, it's going to be referred to as baseline. Now we add object tracking to the model after object detection. We first add a discrete tracker that associates objects across time in an online fashion. Note that our discrete tracker also handles newborn and occluded objects, as these are important for self-driving safety. After object tracking, we get a set of updated object tracks. We then add a continuous tracker that smooths these trajectories. This step has the potential to correct errors made in discrete tracking or object detection. After discrete continuous tracking, for each object, we extract its past trajectory feature and use that to predict the future trajectory. Note that this differs from the baseline model, where motion forecasting exploits the features from the current frame only. To keep track of objects online and for a long-term time horizon, we equip the model with explicit memory of already tracked objects, memorizing their trajectories as well as their features. This enables our model to recover objects from long-term occlusions with real-time state estimation. Before we go into details of the proposed discrete continuous tracker, we first define how to extract the trajectory level representation. This representation is used by both the tracking and prediction models. Given an object trajectory, we first extract a history observation feature, which is defined as a concatenation of object observations at each timestamp. Note that the past VAV feature maps are already saved in the memory. Therefore, the feature computation here involves query operations only, which is done as bilinear interpolation of the object center pixel feature. In practice, rotated array pooling can also be used. Apart from the observation feature, we also extract the history trajectory feature, which explicitly encodes the object motion. Specifically, the trajectory feature is defined as the local displacement of object center positions and orientation in bird's eye view. Given two types of history features extracted, we then merge them frame by frame and extract temporal context by feeding the sequential feature into an LSTM module, which outputs a fixed dimension representation for the trajectory. We choose LSTM for its capability to handle variable length of input data and the ability to capture long-term dependencies. Now we give details of our discrete continuous tracker. We first introduce the discrete tracking, which solves the data association problem between past tracks and current detections. For each past track, there can be two association results. It either finds a success match with a current detection or does not find a match, and therefore we assume it is currently being occluded, as we have to hallucinate this current state. Note that this is important for self-driving, as we need to pay attention to occluded areas in case traffic actors come out of it. For each current detection, it also has two different association outcomes. It either gets associated with a past track or does not, which means that this is a new object coming into the scene. And the second case happens a lot in self-driving scenarios, as the EO car is moving as well. To cover all different outcomes in data association, we combine the benefits of both multi-object tracking and single object tracking. Specifically, multi-object tracking solves for the exclusive assignment between tracks and detections, including the newborn of tracks. Single object tracking, on the other hand, solves the state estimation for unassociated tracks. Next, we explain how we approach multi-object tracking and single object tracking, respectively. We first build a bipartite graph composed of past tracks and current detections. We add the same number of pseudonodes as detections in the track side of the graph to account for newborn objects. We compute pairwise match scores using learnable matching functions. Specifically, we use an MLP that takes both trajectory and detection features as input and outputs a scalar value. We use the Hungarian algorithm to solve for the optimal frame assignment. In the case shown below, we find associations for 2 out of 3 past tracks, with 1 track unassociated. There is also a newborn object here. After multi-object tracking, we then perform single object tracking on unassociated tracks to estimate their current state. Our model design is similar in spirit to the CMS tracker, but replaces the correlation filter with a learnable matching function. In particular, we find a neighborhood in the current frame's BEV feature map, centered at the previous frame object position. Each voxel in the neighborhood is considered as a candidate. We then compute the match score for each track voxel pair with an MLP, given the track feature and voxel feature as input. We find the best candidate by using the Rmax over all matching scores. We argue that compared with simply adopting a motion model for state estimation, our single object tracking approach can produce more accurate estimation as the current observation is exploited to provide helpful information like the map context. For each updated track from discrete tracking, we re-estimate its confidence and smooth the past trajectory. While the first step helps remove false positives from object detection, the second step helps recover association errors made by the discrete tracker. Lastly, we apply NMS to remove duplicated tracks that are highly overlapped. The motion forecasting model of PnPNet is a simple regression-based feature prediction. In general, more complicated prediction models can be applied here as well. The key to the success of the motion forecasting model is the enriched input feature, which is defined as a trajectory representation after discrete continuous tracking. Note that this differs from our baseline model, where the prediction header shares the same voxel feature as at current frame as the detection header. Here we explain how we perform end-to-end optimization of the whole model. We apply multitask loss for detection, tracking, and prediction respectively. For detection, we use the conventional loss function, which is across entropy for classification and a smoother one for regression. For discrete tracking, we apply max margin loss on the affinity matrix. For continuous tracking, we apply max margin loss on the confidence scores and a smoother one on the trajectory refinement. For motion forecasting, we apply a smoother one for feature waypoint regression. Since our model involves strong temporal dependencies, we adopt video-centric training, where we sample video snippets from the training logs as a mini batch, and during training we use online estimations instead of ground truth. Instead of ground truth labels from previous models and timestamps, so that we fully mimic the test time situation. Here we show the results of PnPNet in terms of 3D object detection on the nuScenes benchmark. We evaluate car detection and show from the table that the detection model of PnPNet achieves state-of-the-art performance compared with other 3D detectors. We now look at the tracking results. We achieve 8% gain on the ranking metric AIM-MOTA compared with the state-of-the-art method on the benchmark. We then replace the discrete continuous tracker with a Kalman filter-based tracker and still show a 4.6% gain in AIM-MOTA. What's more, PnPNet also produces more complete trajectories, which is justified by the few SID switches and fragmentations. We also showcase better occlusion recovery capability with more quicker tracks initialization time and much smaller gap duration. Now we showcase the joint P&P results. We show perception metrics in the left plot with detection AP and recall rates, and show prediction metrics in the right plot with prediction ADE and FDE, which corresponds to trajectory waypoint offset average over the future 3 seconds and at the endpoint. We plot relative improvements over the baseline model that doesn't have the tracking model. On nuScenes cars, we show a 2% gain in detection AP and up to 4% improvement in object recall, which mainly comes from occlusion recovery. Thanks to the enriched trajectory representation, we observe up to 9% error reduction for prediction errors. When we apply our model to another dataset, ATG40, with different hardware settings, similar improvements on perception are achieved. We observe a large improvement on prediction with up to 16% error reduction. This is because ATG40 contains a larger proportion of moving vehicles compared with nuScenes. Therefore, the gain of exploiting long-term history is more significant. In addition, to validate the generalization across datasets, we also test PnPNet on pedestrians. where similar gains are achieved in both perception and prediction as well. The results show that the fully learnable trajectory representation and the matching function can successfully learn from data different motion patterns. Here we show some qualitative results of PnPNet on vehicles and pedestrians within 100 meters in ATG4D dataset. Our model is able to produce scalable tracks, even under occlusion, and produce accurate estimation of future trajectories. To summarize, we have seen that neural networks can be trained end-to-end to do detection and tracking. However, for self-driving, we ultimately care about occupied space now and into the future in order to plan a safe maneuver, and this might change the whole game. To address this, we perform joint perception and prediction, which we have shown works better than the traditional pipeline where detection, tracking, and prediction are conceived as sequential and are optimized separately. Finally, we have shown how we can add the tracking in the loop for our end-to-end differentiable framework, achieving the best results. This is all for me today. Thank you.